I wanted to show you again with you know you know 20 years of estimating, cost engineering, and many different types of scopes of work and work breakdowns, different different companies that did vastly different things. Um, just thought I'd explain or show in detail what how I operate and how I become you know usually the in-house expert in different scopes of work or work breakdown structures, if you want to call it that, more so than people who have been doing it almost their whole career. Um, so when my last opportunity, um, they were a steel fab shop. Uh, you know, the owner's been doing it his entire life, and we would have these semi arguments about weld times and how long things take to make. And he was operating off of a very 1980s kind of a mindset of, well, they just threw in half hour a piece here, an hour a piece for that, with literally no backup to where that comes from. Just some basic rules of thumb, because back in the 80s it was a lot of information to try and compile using paper and pencil. So I started down this path to I want to know how long something should take. Um, so you can either know that your estimates are correct, challenge the shop that they're fabricating to some known standards or known values, and then both the shop and your cost models should be in tune with each other, so you're constantly going back and forth and just fine tuning everything. So this this here, so this is a basically figuring out how long it takes to burn plate items. So I went out, did all kinds of research. I found at least some manufacturers what they're stating, um, different cut speeds based on different thicknesses of materials, and then you can basically compile that into this list here where you can you know these are stated values. Now, are they 100% accurate? You don't know until you actually do your own time studies for yourself. So, but you can take this as a guide, which is what I did. So basically, I mean, here it is. Here's the straight cut times, just arc time. I guess you want to call it, or not arc time. Yeah, the plasma cut time, inches per minute, based on, again, some published values that you can look up, and I'm sure these guys study this stuff over and over again, because that's what they do every day. Now you come over here and you build some test models to test these guys, what they're stating their values are. And so here we have a 3/8 plate, 18 by 24, kind of a generic size. Perimeter, I put in 4 holes. You have your cutting inches, total inches, then you have your inches per minute based on 3/8. So I went a little faster. This is at 86 inches a minute. But anyway, this is just save your. Oh, here it is. Plasma table. Anyway, um, straight cut time, but then you're moving it into positions. So the machine obviously you have to uh, start the program, and then it has to move into position. And I probably have a breakdown as to where I got 15 seconds from somewhere. But so now we're looking at some cut minutes for this size plate. Just cutting it out in 4 holes is about a minute, minute and a half. Now this is on a per part thing, removing from the table, clearing the part. Some of this stuff here, then now this is the total all-in fab time. Now this is what I was saying. They would just have a generic 45 minutes each. No thought process into the size of the plate. It was just a complete swag. Um, and so I was trying to benchmark their guesstimates based on actual data. And this, keep in mind, and I tried to explain to them, as quantities go up, as your volume increases, this gap difference has a humongous difference on your, you know, winning projects or losing a lot of money, in if you win a project. But if you know your costs and you know how long things should take, then there shouldn't be a you should know pretty much what your bottom line cost should be. So in this scenario, here we have the same size plate, and I'm including fit up and welding time in this. So here we are, sheet, moving the stock sheet to the table, removing it from the table. This is the scrap and the drop, and then here's your cut time based on this information over here, and then it's just then the information just flows down. So here, plasma table, fit up and welding time. I'll go over that in a little bit. Programming, quality controls included, and then loading. So here we are, some hours of 6.1 hours for 15 plates, and that includes, again, the whole thing: going to get a sheet, bring it to the table, removing everything, cutting it, and then doing your fit up and weld times. So that should be a complete the complete process. Whereas just doing a generic 45 minutes, you can see it's almost double. And now this is a fairly small plate. If this was much larger, well, this could be double this hours. So you'd be bidding, you're lowballing yourself. And then I just run down different scenarios for 3/4 inch plate. Here's some 1 inch plate, 1/2 inch, and you can just see how the times vary depending on the type of material. And that leads me into this welding time. Oh yeah, so here we go. So sheet to the table, removing from the table, and the QC and the programming and all that stuff. So where does that come from? This comes from doing actual time studies in the shop that I had worked at. How long it takes something from and to, and then I'm not going to go into all these details, but I would constantly time, kind of like that process from almost start to finish. So in that specific shop, if I used 10 minutes, that was a pretty good median time for using just 3/8 plate. There's different stock size sheets would take more or less time than this, but in this scenario, just to get a good idea, um, I use 10 minutes. And then you have your weld times. This is another one of those things where I had been, they'd sit there and just look at the drawings and then take a guess, or they'd call somebody on the phone and hey Joe, we got this thing we got to weld, and well, how much time do you think it would take? Just literally just guessing. So again, I compiled a bunch of information of guys who have had years of experience in welding. They had recorded information. You could find some things online, um, some documented information from AISC. So anyway, what I did was I just compiled a bunch of stuff, put them all in these data tables. So we both have how fast somebody can weld on a linear feet, like a lap weld, but then you also have your different kind of joints, and on fillet welds it's more looking at the volume, because it's not always so it's how much volume of the fillet that you're filling up, where these are like single passes. These will be multiple passes, um, and then you come up with sort of, here's your linear your per linear feet per pass at the different, and then here's your, well, this is on a fillets, but it's almost on a pass thing. Um, Again, without diving into this thing drastically, because I might get myself confused. What does all this stuff mean? Again, when you come back to, I lost it. Here's this 3 inches per minute, right? Fit up in weld times then, and that has been shown. It's usually around 4, but I use, this is 5, and then depending on the thickness. So in this scenario, I'm actually fairly slow, but in the estimating world, so now all the information compiles over to the estimate. And the way I develop this program is when you select plate items, doesn't matter what it is. I have to do shoe plate 3/8, again 18 by 24, like in that one scenario. What did I say? I had how many of these? 15. 18 by 24. 12 hours. I'm at 6 hours, I guess. I must have upped the fabrication times. Really not sure. I have to go look. In my database of where the labor comes from, here you have part programming, quality control, loading, handling, saw cutting, drilling, all that stuff. So here's your handling for your plates, burn table and brake, fit up and welding. And then here's your times depending on the thickness of the plate. And then oh, I know. And then there's a size factor. I was trying to tool around with that because if you have a smaller plate or a larger plate, it's going to make a difference. Right? And that's mainly due to the fit up and welding, because if these are just going to be shipped loose where there's no fit up and welding involved, now the times are going to be, And let's see here, if you want to look at how much welding is, here's your different types of passes, or different types of different weld requirements. There's a 6 and 12 really. So a 12-foot piece, this would be a lap weld. Do a continuous, then depending if you have to have 2 passes. All right. So here's your hours. Now these are standard. This is at the optimal weld. I guess between your waist and your shoulder height, I guess. It may be a requirement where it's vertical, which is, from what I was told, it's usually like double. This times 2. So did that work out right? Yep, it's exactly double. Then you have to also look at it could be in the field. So the field is basically, I don't want to go over this, but anyway, the field is usually double what the shop is. And where I was, they had talked about man days, so over here will be the man days. That will be in the for the field erection requirements. Let me see here. One of the things I think is on maybe in the one video is about, again, doing time studies, and then how that equates back into doing your estimating, doing your building your cost models. Was the drill line, drilling holes. Let's see here. Yeah, so this is again doing my own time studies. looking at how long things take to drill. Here's all the different items that were drilled, number of holes, size of the hole, and all that. Comes over to here for how much. Then what do they equate to in well, in dollars, but how much time per hole on average, and then flowing, having the information flow over to your consumables, your machine cost, shop labor. Then you're down into how much is each hole cost the company, and then you have your sell price and all that stuff. And so on beams, actually, I'm gonna make this 100 so you can see something here. So what this does is this right now is not an erected item. It's just a straight beam that's being cut at 15 feet, 100 of them. That's how many hours. That's again the whole process of moving something in, handling, saw cutting. Oh, there's drilling. That shouldn't be there. It should not be there. Anyway, this is going off of because where I was, they were a bolt shot. All the connections were bolted. So this takes this size beam and its sides, and it automatically counts up the number of holes, and then puts on the drill times accordingly. Again, based off of historical data, real information, not guessing. And then you'll notice if you go to a much larger beam, same quantity, same length. Now we have saw time is much greater because it's a much larger beam. Handling time is much slower. It's much heavier. Drilling time is much slower because of the thickness that you're drilling through. But and again, this right now, it used to be if this was a picked item, then it would select. Let me see this. If I delete that, I gotta check into that. It's supposed to only put in the drill time if it's a picked item. Huh. Well, I'll look into that. Um, yeah. Well, anyway, I'm just gonna show you, I guess, number one, how I operate and what I did. This one specific company. I've done this for, you know, at least this one plus four others. Just that now with today's technology, you can record things, and I didn't have that available to me, years ago. Um, so hope you learned something about maybe what I can do for you.